Accelerated Chemistry students, and this is Ms. Crisafoli, and this is your Chapter 8, Section 3 notes all over bonding theories. So let's talk about molecular orbitals. The models you have been using for covalent bonding assumes that the orbitals are those of the individual atoms. There is a quantum mechanical model of bonding, however, that describes the electrons in molecules using orbitals that exist only for groupings of atoms. When two atoms combine, this model assumes that their atomic orbitals overlap to produce molecular orbitals or orbitals that apply to the entire molecule. In some ways, atomic orbitals and molecular orbitals are similar. Just as an atomic orbital belongs to a particular atom, a molecular orbital belongs to a molecule as a whole. So a molecular orbital that can be occupied by two electrons of a covalent bond is called a bonding orbital. So let's talk about some sigma bonds. So when two atomic orbitals combine to form a molecular orbital that is symmetrical around the axis connected by two atomic nuclei, a sigma bond is formed. So basically what happens here is that we have two s orbitals. Remember our shapes of orbitals, s, p, d, and f. So when we have two s orbitals that overlap, a sigma bond is formed. And it is given the Greek letter sigma. So when two atomic orbitals combine to form a molecular orbital, so sigma bonds exist when covalent bonds result from an imbalance between the attraction and repulsion of the nuclei and electrons involved. So the nuclei and the electrons attract each other, and then the nuclei repel each other. And then the electrons are also going to repel each other. So in a bonding molecular orbital of hydrogen, however, the attractions between the hydrogen nuclei and the electrons are stronger than the repulsions. So the balance of all the interactions between the hydrogen atoms and thus tip in favor of holding the atoms together. And this results in a stable molecule of H2. So atomic p orbitals can overlap to form molecular orbitals as well. So when we look at fluorine, it has a half-filled p orbital because there's only 3 electrons in the p orbital. So when two fluorine atoms combine, the p orbital overlaps to produce a bonding molecular orbital. So there's a high probability of finding a pair of electrons between the positively charged nuclei of the two fluorines. The overlap of the p orbital produces a bonding molecular orbital that is symmetrical around the FF bond axis that will connect the nuclei. Therefore, the FF bond is also a sigma bond. So let's talk about pi bonds. In a sigma bond of fluorine, the p orbitals overlap end to end, and in some molecules, orbitals can overlap side to side. So when we look at a p orbital overlap, we call them pi bonds because you have two lobes and they're going to overlap on the top and on the bottom, and they're going to form a pi bond. So in a pi bond, symbolized by the Greek letter pi, the bonding electrons are most likely to be found in a sausage-shaped region above and below the bonding axis. And because the atomic orbitals in pi bonds overlap less than in a sigma bond, pi bonds tend to be weaker than sigma bonds are. So let's look at the electron dot structures, and then let's look at how that translates into from 2-dimensionals to 3-dimensionals. So electron dot structures don't reflect the 3-dimensional shape. They only look at the 2-dimensional or flat shape. So in reality, all molecules are 3-dimensional. So what happens is that the hydrogens in the methane molecule are at the 4 corners of a geometric solid called a tetrahedron. So this arrangement is what we're going to call tetrahedral. In order to explain the 3-dimensional shapes of molecules, we use what is called the VSEPR theory, which stands for valence shell electron pair repulsion theory. So it basically states that the repulsion between the electron pairs will cause the molecular shapes to adjust so that the valence electron pairs stay as far apart as possible. So we can have unshared pairs of electrons that will also help us. So you'll see that when we draw ammonia, you'll have those 2 dots on top of the ammonia molecule that will not be in a bond. And what they do is they will also repel the electrons in the bond and make that molecule have a different shape. So those unshared electron pairs at the top are going to push the hydrogen-nitrogen bond down, and that is going to make them have a bond angle that is less than what the tetrahedral angle would be, which would be 107 instead of the 109.5. In a water molecule, the two bonding pairs and the two unshared pairs of electrons form a tetrahedral arrangement around your central atom. Then what happens is, because we have two unshared pairs, that molecule is actually going to be bent, and that bonding angle is going to be even less than that, and it's going to be 109. Instead of 109.5, it's going to be 105 degrees Celsius. The carbon in a carbon dioxide molecule has no unshared pairs around it. So when we line these things up, it's actually going to be linear, which will have a bond angle of 180 degrees away from each other. So these are all your possible VSEPR shapes. Okay, we're going to talk about this a lot more in detail when we build these molecules next week in a lab that we're doing. So sit tight for right now and just understand that VSEPR theory allows for us to draw molecules in 3D based on how the electrons are going to repel within the bonds, and then the non-bonding electrons are also going to repel. And so these shapes are going to look different. So VSEPR theory works well with accounting for molecular shapes, but it does not help much in describing the types of bonds formed. So hybrid orbitals is how we would do that. So orbital hybridization provides information about both molecular bonding and molecular shapes. In hybridization, several atomic orbitals mix to form the same total number of equivalent hybrid orbitals. So let's look about sigma bonds. So carbon's outer electron configuration is 2s2, 2p2. But we already talked about it, that the 2s2 and the 2p2 are going to combine to make 4 orbitals of the same energy. So then what happens is that the 2s and the 2p bonds are going to be identical. So we're going to make a sp3 hybrid orbital, and that orbital is going to allow for the electrons to be at the tetrahedral angle of 109.5. So what happens is that the 4 sp3 hybrid orbitals are going to overlap with the 1s orbitals of hydrogen. And we are going to create sigma bonds where those orbitals overlap, and that's why they're single bonds. So the sp3 orbitals extend farther into space than either s or p orbitals. So that allows for a great deal of overlap with the hydrogen 1s orbitals. So, and this extent of overlap results in unusually strong covalent bonds. So let's talk about double bonds. So ethene is a relatively simple molecule that has 1 carbon-carbon double bond and 4 hydrogen single bonds. So what happens is the sp2 hybrid orbitals form the combination of 1 2s and 2 2p atomic orbitals of carbon. So each hybrid orbital is going to be separated by an angle of 120 degrees. So what's going to happen is this picture is going to result. So we have the 1s orbitals from the hydrogens, and then we have the s's and the p orbitals from the carbons. So what we're going to do is we're going to make a pi bond and a sigma bond. So a double bond consists of a pi bond and a sigma bond. So in ethene, the 2 sp2 hybrid orbitals of each carbon form sigma bonds, molecular orbitals with 4 available hydrogens, and then the third sp2 orbital of each of the 2 carbons overlap to form a sigma bond orbital. And then the 2p are going to overlap to form your pi bond. So let's look about the triple bonds. So a third type of covalent bond is a triple bond found in ethine, and it's also called acetylene. So it is a linear molecule. So what's going to happen is the hybrid orbital is going to be obtained if the 2s and the 3 2p molecules mix. So then this will result in 2 sp hybrid orbitals for each carbon. So what that looks like is in the picture below. So we're going to have the 1s and we're going to have all those p's. So what happens is that your sp hybrid orbital along the axis is going to overlap and forming your sigma bonds. Then you're going to have the 2 p's on the top, and then the ones front and back that are also going to overlap to form your pi bonds. So in an ethine molecule, 1 sp hybrid orbital from each carbon overlaps to form a sigma bond, and the other sp hybrid orbitals of each carbon overlap to form another sigma bond, and then the two p orbitals are going to overlap and form your pi bond. And as always, thank you for watching, and this is the end of your Chapter 8 Lesson 2 notes. And as we've said in every single video, all of the information on these Google Slides has been acquired and adapted from the Pearson Chemistry's 2012 edition textbook resources CD and pearsonchem.com. Thank you so much, and have a good night.